Good afternoon. Good afternoon. On behalf of the Vice Chancellor and Principal, Professor Nana Poku, it gives me a pleasure to welcome you to the inaugural lecture of Professor Thomas Konrad. The Vice Chancellor conveys his congratulations and best wishes to Professor Thomas Konrad. The Registrar, Dr. Kathy Cleland, extends her sincerest apology for not joining us today. The Registrar conveys her congratulations and warm wishes to Professor Konrad. Inaugural lectures form part of the University Public Lecture series and may only be presented by newly appointed full professor who have been appointed in academic school and centers. Inaugural lectures present an opportunity to showcasing the exciting and groundbreaking research and teaching being carried out by professors in our university. Each lecture represents a significant milestone in an academic career, providing official recognitions of their promotions and appointment to full professorship. And these lectures are furthermore an ideal opportunity for new professors to introduce themselves and to present an overview of their own contribution to their field to academic peers, students, and research collaborators. Inaugural lectures are also a platform for celebrating a professor's academic achievement with his or her family, friends, mentors, and colleagues. I would like to acknowledge the following guests: the members of executive management, members of Senate, our inaugural this afternoon, Professor Thomas Konrad, family and friends of Professor Konrad. Special welcome to Professor Konrad's father, Professors Alios Konrad, partner of Professor Konrad, Pamela, and daughters Melly, academics and professional staff, students, alumni, and distinguished guests. It is my pleasure to introduce our Dean and Head of School of Chemistry and Physics, Professor Ross Robinson, who will now formally introduce the inaugurant, Professor Thomas Konrad.
Thank you, Professor Madal, and good afternoon, ladies and gentlemen. To those of you online, welcome as well. And to those in the auditorium, thank you for joining us today. It's a great pleasure for me to have the honor of introducing my friend and colleague, a member of the School of Chemistry and Physics, to give his inaugural lecture this afternoon. Thomas Konrad studied physics in Tübingen, London, Rome, and Constance. He holds a Master of Science from the Eberhard Karls University in Tübingen, Germany, with a dissertation in celestial mechanics, a Master of Science of the University of London Imperial College in quantum field theory, and a doctorate in theoretical physics from the University of Constance. He joined the University of KwaZulu-Natal in 2006, and during this period, he served on the Council for the South African Institute of Physics, SAIP, for 2 terms as the editor of the SAIP online journal, Physics Comment, for a period of 2012 to 2017. He is currently a member of the University's Senate and the academic leader for the physics cluster on the Westville campus. Thomas Konrad pioneers research in quantum information processing and communication. He is an internationally recognized researcher with an NRF B rating. Konrad promotes the interplay between science and art and brings science into the public realm in newspaper articles and radio interviews. Ladies and gentlemen, it is my great honor this afternoon to invite Professor Thomas Konrad to deliver his inaugural lecture. Professor Konrad.
Deputy Vice Chancellor, Professor Madal, Dean and Head of School, Professor Robinson, dear colleagues, dear students, dear ladies and gentlemen. It's my pleasure to give this inaugural speech today, inaugural lecture. And I want to formulate today 3 theses on quantum information processing in communication. And with these 3 theses, I want to tell you 3 stories, 3 journeys on which I want to take you, because the theses are just the end product of a long journey of each of them. And each journey starts at home. And this is my family in Germany. Family reunion, gathering. Wonder whether you can see my pointer. No, not yet. So here you see my partner Pamela Ben-Porras and my daughter Merle, and various members of the family. My father is in the audience. Okay, if it is a scientific journey, and that is what I want to talk about today, then first of all, you need teachers. And while I did my master's in Tübingen, I had very good teachers. You heard it just from Professor Madau. It was in celestial mechanics. And I worked under the supervision of Professor Michael Soffel, who is an astrophysicist, and Professor Victor Blumberg, who spent his Humboldt Fellowship in Tübingen in that year. And he has the reputation that he is the last living celestial mechanic. Since celestial mechanics becomes more and more out of fashion, celestial mechanics used to be a very big area of physics, of astrophysics, where people calculated the orbits of stars and planets in an analytic fashion. But nowadays we do a lot of things with computers. Then I went to the Imperial College to do a master's in quantum field theory. And here I want to thank Dr. Hugh Jones, who introduced me to non-perturbative methods in quantum field theory. And I believe he's also in the audience today. My PhD I did in Constance under the supervision of Professor Dr. Jürgen Audrich, an expert in the foundations of physics and quantum optics. And there I also met Professor Lajos Diogi, who became my teacher as well, I must say. And I think it doesn't matter how old I get, I will always be a student to Lajos. Of course, you also need students if you go into a scientific journey. And here's a picture of some of them. And I also want to thank them because they taught me a lot. So 3 theses on quantum information processing communication today. The theses are: quantum systems can be robustly controlled by other quantum systems. Optical images can be teleported. Not all quantum computations can be simulated using only classical light. What is this all about? Well, the first thesis is about control, quantum control, and that means the control of atoms and photons. And here you see a device that allows us to measure the time very precisely, atomic clock. And these atomic clocks are now by default on satellites that allow us to position ourselves, so GPS satellites. And some of these atomic clocks are so precise that you can, that they don't lose or gain 1 second in 15 billion years, which means it's longer than the age of the universe. If you had such a clock started at the beginning of the universe, at the Big Bang, then it would still have not lost a second. There are other devices where you need extremely precise measurements, and one of them is mapped down here. So this is an apparatus that allows us to measure how the gravitational field couples to masses that possess quantum mechanical properties, and we investigate what the influence of gravity is in quantum physics or on quantum systems. And in order to do these things, you need extreme control of atoms and photons and nuclei and other particles, other quantum mechanical systems. The second thesis is about quantum teleportation, and that is a tool that we need in quantum communication. So here you see a network in China that is approximately 5,000 kilometers long and has around 50 nodes. And there you can securely communicate using single photons from one node to the other. The nodes themselves must be trusted partners in this, because there you read things out and then you reprogram it and send the next message to the next node. And in order to have non-trusted nodes, we would need this process of quantum teleportation, because it allows us to transport quantum systems, or the state of quantum systems, more precisely from one node to the other. Okay, so the last thesis will be about quantum computation. And quantum computation is a field that is still in its infancy. What you see here is a quantum computer that is based on trapping ions and manipulating them in order to calculate things. And it is supposed to be a technology that will be much faster than the usual computer that we currently have. But in order to do that, we need, I would say, at least 10,000 error-corrected qubits. Qubits are the basic storage units of such a quantum computer. And here you see a timeline for IonQ. That is a quantum computing company that works with these ion-based quantum computers. And you see they have now 22 or 25 qubits that are error-corrected. And they want to go on here in the year 2025. They want to have 64, and the two stars here mean this employs error correcting encoding that needs 16 additional qubits for each qubit, physical qubit that you have there. And then it goes on, and it is supposed to reach 1,024 in the year, so before the end of this decade. So this is in its infancy, and there again you need a lot of control and techniques from quantum physics. So let me come to my first thesis, and this is about quantum control. And in order to show you what quantum control actually is, I display here an experiment that was done in Paris by the group of Serge Haroche, who obtained a Nobel Prize in 2012 for his precise experiments. And what you see is on the right-hand side, there is an oven that emits atoms that are in a special state, a so-called Rydberg state. That's a state where the electron is very, very excited and goes on orbit, more or less classical orbit around the nucleus. And these atoms, they fly here through a cavity, and their task is to measure the number of photons in the cavity. Okay, and photons are the excitations of the electromagnetic field. And you can imagine that if you have an electron that is very far from the nucleus, that it reacts very sensitive to electromagnetic forces. And this is what is used here in order to change the state of these atoms. And then they can be detected. The state change for the experts amongst you is a relative phase shift, a so-called AC start shift. And this can be detected by interferometric technique here with these two cavities, extra cavities, called Ramsey interferometry. And at the end of this process, you can say something about the number of photons in this cavity, but it's not very precise yet. If you only detect a single atom, you need many atoms to get a precise estimation of the number of photons. And now you can use this and connect it to a controller. So here is a controller. That is a unit that calculates from the detection signals what is the estimated number of photons in the cavity. And then it compares it to a set point. Let's say you want to have 5 photons in the cavity. Do I have 5 photons? If not, then it starts this actuator, which is basically a unit that's just pumping electromagnetic pulse into the cavity and fills it up if should there be photons lost. So what happens in this process here is that the number of photons can change in time. Why? Because photons can leak out of the cavity, or photons can come in from thermal radiation from the environment. So as a result, we can see here in this experiment that the measurement signal shows you atoms that were detected in the excited state, or sometimes there were 2 atoms detected in this excited state, and sometimes they are detected in the ground state, and that carries information about the number of photons. And here is a difference function that calculates the difference to the set point. And each time when the difference is very high, it starts a pulse. So you see here this pulse, and then the number of photons is filled up. And from simulation, we see here how the number of photons is varying. It's quite interesting here. A photon leaked out at approximately 25 milliseconds. And then later, there is a photon that actually comes in. So at a certain point, we have 2 photons in the cavity. That's a photon that comes from outside. And in each instance where the photon number is not right, we start a pulse in order to get it to the right level. So this is quantum control in action. However, as you can see, it's very shaky, the signal. And here's another example where they control it at 4 photons, and it's also very shaky. So the question arises, can we do better than this? And this is the first journey on which I want to take you. It talks about state monitoring based on consecutive measurements, then about measurement-based quantum control, and in the end, about the control of quantum systems by other quantum systems. So should we not get to the end of the 3 stories, which could happen, then please don't worry. I'd rather tell you each of the stories in a consecutive or an understandable order. And yeah, let's continue. Let's go in medias res. So this is the story of that started during my PhD with Professor Aldrich. And we looked at a system that was quite similar to the system of Harosh. In fact, we took the papers of Harosh in order to calculate and to analyze the situation. And here, the only difference is that we have a double cavity where the photon is supposed to oscillate between the 2 cavities back and forth. And we want to measure the oscillation. Okay, so the photon is not leaking out, its oscillation is, in a theoretical sense, a more clean situation. It's easier to calculate. And then we found out that if you measure too strongly, that means if you send either too many atoms through the cavity, or you make the coupling too strong, there are means to increase the coupling by additional electric fields. Then you see this first curve here, which shows you here a simulation of the probability to find the photon in the upper cavity. So in the beginning, the photon is in the lower cavity, then it makes a jump, and then it stays in the lower cavity, then it makes again a jump. One could call these jumps quantum jumps. This is really a good example for this. So forth, but it tends to shelve. So the stronger you measure, the longer you will stay on one of the levels, and then you make these jumps up. And what happens is that the natural evolution, which would be something like an oscillatory motion, is totally disturbed. So the opposite, this is, by the way, known, the fact that you suppress the motion of a quantum particle if you measure it too hardly, is known as the quantum Zeno effect, and it's an instance of a watch kettle never boils. Okay? So now the opposite of it is if you measure too weakly, then you don't disturb the system much, but you also don't get much information about it. So you can see that the measurement signal here is widely varying. And in the intermediate regime, where you measure on a time scale that is related, so on a level resolution time that is related to the Rabi oscillation, was nearly equal to it, Rabi oscillation period, then you see that these shaky curves that we saw already with Harosh. Okay, so here the motion is still recognizable, but there is an influence on it, and the measurement signal is quite correlated to the motion. And what we then did, so this was the first step in trying to make it better than Harosh, to get a better signal and to disturb maybe less. And a big step came about when Lajos Diósi told us how to actually treat the problem in an analytic fashion. And that involves that you make a transition from the sequence of measurements to continuous measurement. And continuous measurement means here just analytical description. So you are not changing the actual measurement sequence, which is still discrete, but you just treat it in a continuous fashion. And the way to do that is to treat it as if the time between the measurements would go to zero, and the measurement strengths would also go to zero. And if you do that in such a fashion that the quotient of both quantities that should go to zero, I'm sorry for this here, this should be going to zero. If the quotient is still reflecting your discrete ratio, then you can describe the whole thing in a continuous fashion, in a smooth fashion. And that means you can write down differential equations. And once you can do that, then you have the problem under control, or at least much better under control. And the second thing that we learned from Lajos was that we can actually write down an estimate, and we can propagate the estimate in the same way, so the estimated state, we can propagate it in the same way as the real state of the system, namely using this differential equation. And then something very curious happens, and that I want to show you in the movie. So here we have two wave functions. So I have to explain what a wave function is, maybe. So if you have an atom, then usually you cannot precisely say where you will measure it. So if you measure its position, it's not clear, will it be at this position or at the other. And then you can give a probability distribution. And this probability distribution is encoded in a wave function. Here you see the probability distribution of the particle that is in some potential, trapped in some potential, and another wave function or another probability distribution for the estimated state. And then this real particle is measured, while the estimate is just something on my piece of paper that I will update according to the measurement results. So if I do this, maybe I have to say one more thing, namely this potential here is very difficult. It leads to a very complex motion because it's a chaotic potential. So points that would be close to each other can, after finite time, be very far from each other. And now we start the stance of the two wave functions, or the two probability densities more precisely. And you see that they soon overlap quite nicely. Here on the left-hand side, you see a measure for the overlap, or the measure of how close they are to each other. It's called the fidelity. If it's 1, they are absolutely identical. And now what happened was that the particle got hit by another particle and flew away, and our estimate has to run after it in order to find it again. Okay, but since the measurement results kind of reflected the real position of the particle, the estimate can follow it. And maybe I can say here that this can be seen if you ask me, why is it that all probability distributions under the same sequence of measurement results converge to the same probability distribution? Then this is an instance of Bayes inference. So if you are a Bayesianist and you look at probability distributions, then for you they are just subjective degrees of belief. They correspond to betting quotes. And if you are at the beginning thinking of different quotes, but you collect evidence, then your probability distributions will come closer to each other and will actually converge if you have an infinite sequence of evidences. So under the update of a probability distribution, which is given by something called Bayes' law, all belief systems that are rational, in some sense, probability distributions correspond to rational beliefs, and because they follow the three axioms of Kolmogorov that correspond to logics in some sense. Or if you're rational about your beliefs and you follow the update, then you will end up with the same beliefs. This is a big triumph of for rationalism, and it is, in a strong mathematical sense, only valid under certain conditions, and namely, you need a finite probability space, and it must be dense in a certain sense. Okay, so this is why they converge, and here's a photo of Hermann Eyes, a colleague of mine with which I worked together for a long time, and he used this to estimate the state of the internal state of trapped ions. So if you have ions that are trapped, then there is always noise from the environment. So, for example, there could be some phase noise, and after a certain time, you don't actually know whether the ion is up or down because of this phase noise, but you want to know this. Okay, so this is a big thing, and using our method of estimating the system with this very smooth method, using the differential equations, we could actually show that the estimation fidelity, even in the presence of noise, is very high. Okay, so this is a good method. And before I come to this slide, I want to say that Hermann now works for IonQ, that is the company in the US that produces these computers that I showed in the beginning. Therefore, we cannot, at least with him, realize our dream to build an atomic clock that is based on this a new measurement and estimation technique. But before he went, he made a very important, or he posed a very important question, namely the question whether atoms can be controlled by other atoms. So this is now, we go to a different realm. So far, we had always measurement apparatuses, and we had to always measure the system, and in some sense, connected to the outside world, to the classical world. And what we want to do now is we want to design systems that can actually find their way in the quantum world themselves. So how is that supposed to work? So here you have an image of an atom that maybe has two energy levels, and you want to control its state, and then you scatter a sequence of other atoms of it. And if you design the interaction in a way that you design it in such a way that you can drive this atom into a target state. You could even drive it into target dynamics. And how is that done? You must basically think of the atom kind of being the controller and the measurement apparatus in one go. So it senses via the interaction the other atom and then pushes it in a certain direction, depending on where it is. And this was the idea that Hermann had, and he asked this question, and the answer is yes, we can. And here is an example of how we can. This is a picture of my student Amy Rouillard, who is in the audience and who did the simulation here, and also calculations that show the state space of a two-level atom. You can think of it as a sphere. And now if you have a certain interaction with the outside atoms, then the sphere shrinks, okay? And it shrinks more until it's only in one point. And this point is then supposed to be the target state in which you want to have it. All right. So this is the principle, and it really works. One can engineer a partial swap that brings the atom and the controller in a superposition of its original state and the swapped state. And then if you interact with further controllers, you get closer and closer to the target state that was initially programmed into the controller. And this is just an example. And since I made this thesis and I have mathematicians in the audience, I want to present a convergence theorem. So for those of you that are not used to the language of quantum mechanics, don't worry about this slide. In a moment, I will go to to a different explanation. But here you can get a flavor of how this is described. So usually in quantum mechanics, we have the state is described by an operator, so-called density operator, and this dollar of rho is the state change after interaction with an atom. So here you have the atom, the state of the atom rho, and next to it is the state of the controller. And this U here is a unitary operator that maps the system onto the state after the interaction. Okay, and since you're not interested in the state of the controller, you trace out the degrees of freedom of the controller, and then you get a map that can be written in this form here with so-called cross operators that are given here by this expression that depends, of course, on the interaction. And now, if you so every map of interactions of two particles or of two systems can be written in this way. And now, if you impose a fixed point condition for the cross operators, namely that the target state stays invariant because you don't want the target state to change, then you can show that the fidelity that is the overlap between the state as it was before the interaction and the state of the system as it is after the interaction, they come closer to each other. Okay, and the difference in the fidelities is greater or equal to 0. So this leads, with this lemma, you can prove the following theorem, then that if you have such cross operators and the span of this expression here is the whole Hilbert space, this is a uniqueness condition. So it means that there is only one state that obeys this fixed point condition. Then you have something like a fixed point theorem, and you can prove that if you take a sequence of interactions that you will end in the target state. So this is the point here, and this is my first thesis. We can also show that it is that it is resilient to noise. I don't want to go into this now. I want to just come to the discussion of this point. So here the point is that we didn't need measurements. The control happens purely inside the quantum world. And that leads to the possibility that we have an autonomous control. So we can have systems that define their target states themselves. The target states could be coming out of quantum computation, right? So, and this was, I think, Hermann's idea in the beginning, that he had this idea that he constructs a small vehicle that is made out of quantum systems, and they can somehow drive in this quantum world. Okay, and in principle, this can be done. So the other point is that one can use this because with weak measurements, if you do many enough, if you have weak interactions, not measurements, if you have weak interactions and you take many of them, then you get into the target state. So, for example, if you are looking at gas of atoms and you want to prepare them in a certain state, then you send many photons. And even though the photons might couple very weakly to the atoms, because the atoms are moving in all directions, there's Doppler shift, you can still control it. So this is the idea. Here is a slide about the application in optics that I just want to show together with Sandeep Goyal, Amy Ruyar, and Tanita Permaul. We developed a scheme that enables us to prepare photons in certain modes without measuring them. You know, with photons, it's absolutely imperative that you don't measure them, because then you lose them. Or if you want to measure them, you have to do it in this Harosh way, which is very complicated. Okay, so let me come to the second thing. I see I don't have many minutes, so I want to make this short. And the second thesis was about teleportation, and it starts again with a story, namely the story of twisted photons. So twisted photons look like this. Before I come to it, these twisted photons, this whole subject was introduced to me by Andrew Forbes from WITS, who came in 2008. We met and he showed me this paper, Twisted Photons, by a colleague of ours, Juan Torres, from Barcelona. And he said, can we do something with this? And yes, we looked at it. And in the end, what came out is this teleportation, but it's a long story. And let me just tell you what this is about. So usually if you have photons, often the electromagnetic field comes as a plane wave field. That means on a transversal plane, the electric field is constant, but you can twist it now in such a way that you get this kind of corkscrew field, where the field is on the surface of a corkscrew constant and carries orbital angular momentum. And now this is done by applying phase shifts that depend on the azimuthal angle. And these phase shifts lead to orbital angular momentum per photon minus 3 h bar. This is if you have a left circular screw, or plus 3, plus 1, whatever you want, if you have a right circular screw. And this is not to be confused with polarization, where you have also circular polarized light, but this has nothing to do with the polarization. It's just the wavefronts of the modes look like this. And what can we do with this? Well, we can encode information. So if you have photons and you want to transport information, usually this is done with polarization. Polarization has only 2 polarization directions. You could have left and right circular polarized light as a basis, but here we have an infinite amount of basis elements. So in principle, we could put infinite amounts of energy, of information in this. But of course, this is in the end not true. And this we will find later. But for the moment, I just want to point out to you that there are different teleportation schemes. If you want to teleport now a basis of ORM states, and here is such a scheme where you first sort the light according to which ORM mode, so orbital angular momentum mode, this corresponds to this twisted light, it has, so L equal to 1 or L equal to 2 and so forth. And then you teleport each of the mode in some way. This is a scheme called quantum scissors. I don't have time to go into it. And in the end, excuse me, you take an inverted sorter, so-called mixer, and then you get back the state that you had. And what that basically means is that somewhere a state is fed in, and at the other side it comes out without that the actual information traveled between the 2 points, because the only thing that travels here are these extra photons. Okay, so you also need some classical channel to say when you got the right measurement results. But apart from that, there is no signal to the other side that could convey anything about the state of these photons. There are other schemes. I don't want to go into it. The main point is to say that all of these schemes take the extra photons. So if I have the different levels, so I have a photon that has now a wavefront that corresponds to D basis states, where D can be a number, let's say 100. Okay, then I need 100 extra photons. And this is a problem. And why is this a problem? Because here we have such our first experiment that we put together with Jonathan Leach and Steph Root. This is a design that we all three did. And then he converted this to an experimental table. And you see there's quite a lot of optical elements on this. And now if you have to do this D times, then that is D times this table, more or less. Okay, and that's D times the cost of a Maserati. Okay, and then you see that this is basically out of the question. So what we did is we went to a different possibility for teleportation, and that is the possibility to use nonlinear optics. Okay, in nonlinear optics, you have, for example, 2 light beams that come into a nonlinear medium, a crystal of a certain kind, and then the electric fields that you see here, they are multiplied. This is a very nice method of bringing something new in, and this can be used to do one of the components of this measurements. I mean, this measurement here corresponded to a projection onto a certain entangled state, and such a projection can be done if we use these 2 beams, incoming beams, and project here onto a certain state. And here is the setup. Which has a pump beam that produces an entangled pair of photons for the experts amongst you. And then here is a photon whose mode you want to transfer to the other side. And you have these 2 photons going into another nonlinear crystal and a measurement. And after that, the state of the photon, or the mode, the light mode of the photon, will appear here. And what that means is actually that the picture, the image, the optical image is transported to the other side without any information about the image traveling directly from this space, from this point in space to the other point. Okay, this is the teleportation of images, and it really works. I don't have time to go into the details, but here you can see if both of them are L equal to 0, and this is L equal to -1 mode, then they must add up to L equal to 0. So this must be L equal to 1. And also these 2 must add up to L equal to 0 because of angular momentum conservation. And then you get the same mode out as you put in. And since this works for all basis modes and the thing is linear, you can do it for any picture that can be decomposed in these modes. Okay, there is a longish calculation about the bandwidth of this, but I don't want to go into details. You can look it up in a picture, and we did several tests to show this, and we showed clearly that it lies above the classical limit that we can do. And this brings me not to the end of the journey, but to the end of the journey that I can, part of it that I can tell you today, because there are other things. We want to go much further. We want to use bright states of light, so coherent states of light that we can, the images of which we can transport to the other side. And then you can watch Netflix over this teleportation thing. But more than that, we also want to, on a serious note, we want to transfer at the same time the photon number state in it. So there is also superpositions of different excitations levels, and we can combine all this together. And yeah, so this is what we want to do. And there's the team here on the last place. You haven't seen. This is Akshay Dorupasad. He's working on something related to this. Okay, so how much time do I have? I think I'm pretty much at the end. Is that correct? Do you give me 2 minutes? Then I just jump to the last slide for my no, maybe let me go further. Okay, so basically what we did is we showed in several papers that it is possible to at least simulate quantum computation with classical light, but it is only possible to a certain degree. And the problem with it is, in the end, this one, namely, sorry, one slide too much, namely, we can do efficient preparation and measurements with the light. That is possible. So with optics, classical optics, with gates, whether we can do all gates perfectly or efficiently, I don't know. But for those algorithms, quantum algorithms that we looked at, yes, we could do it. But the issue is with the storage capacity. And the storage capacity is like this. When I was a young researcher, I thought the electromagnetic field, this is just a mathematical function. So in each point, I have an electric field vector. And this can vary arbitrarily, but this is in practice not true. In practice, there is a limit, and the limit comes from the wavelength. So the variation on the transversal plane is limited by the wavelengths of the field. And if you want to have a very small wavelength in order to get a lot of information into your light beam, then you have to pay a high electricity bill, because the energy of your photons must be very high. Okay? So that is the problem with this approach. It really, amazingly, it doesn't fail because of missing gates or missing preparation and measurements. I cannot really say that all gates work, but at least in terms of the preparation measurement, I'm quite sure it's efficient. But it fails because of the storage space, the missing storage space in classical light, which you have in quantum light. So if you have photons, then each photon can carry a different spatial mode and different polarization and so forth, and then you have enough storage space. So with this, I come to the end, and I thank you for your attention. This was quite a journey to go with you through this. Maybe my conclusion from all this is that, the journeys in science, they are usually not going on straight paths, but you have to take very many deviations until you find the right idea to do something better. All right. So that's the one thing. And the other thing is that you need a lot of collaborators that can help you in this and that can educate you. So there's an old proverb that says it takes a village to raise a child. I would say it takes a whole research community to educate a scientist. Thank you very much.
Thank you so much, Thomas. I would say that it takes Thomas' father to raise Thomas of this caliber. We have actually learned a lot today, colleagues. I've learned that the quantum information processing starts around lunch or dinner. And I like that. And that's how science starts. And we've learned today about the quantum computing roadmaps, the fidelity functions, the convergence theorems, the weak swap, twisted photons, and teleportations with the nonlinear photons. I think if I was a student of Thomas caliber, I would have been getting cum laude or summa cum laude. That tells you that I was listening very well. But on behalf of the university, I would like to thank so much Thomas for such an exciting lecture. I always say that to raise professors of this caliber at university is something that we should be proud of scholarship of this nature. And as a university, we're very happy of Thomas scholarship and engaged scholarship of this caliber. And on behalf of the Vice Chancellor and this Council, we thank you so much and we wish you best in your future endeavors. We want to breed more Thomas, and I thank you so much.
Thank you.
Well done, Thomas. That went well.
Thank you.